Welcome, Algebra 2 students, to the homework help video. These 3 pages right here and these numbers. Let's go ahead and jump right into this. Let me grab my math book and go ahead and turn over to page 424. So give me just 1 second to do that. And here we go. Number 45 says that you're depositing $600 into an account that gives you 7% interest compounded continuously. What is the balance after 5 years? Well, here we go. First of all, here's your formula. You should know this by now. This is your compounding continuously formula, okay? So, this is my ending balance, A. That's what I'm looking for. So I'm going to leave that A. B is your principal or your starting amount. That's 600. E, of course, is just E. R is your rate, which is 0.07. I got that from right here. T is 5 years. So with your calculator, well, first of all, if you will type into your calculator 0.07 times 5, which I'm doing right now, you will get 0.35. So really your exponent is 0.35 when you multiply those two numbers together. Now with your calculator, type in 600, then hit your E button and this will pop up. And then type in 0.35, close your parentheses and hit enter. And you will get the correct answer, which is $851.44. So you started off with 600. You ended up with this much, so you gained $251.44. Alright, okay, moving on to number 46. Same type of problem again, guys. You deposit $12.50. Your rate is 6.5%. You're leaving in the bank for 8 years, and it's compounded continuously. Now listen, if it was any other type of compounding, quarterly, annually, monthly, whatever, you would use this formula here. But when it's compounded continuously, that's the one time you use a different formula, alright? And of course the formula is the same as the last problem, which is this right here. A equals PE to the RT power. A is your ending amount or your balance, which is what we're looking for. P is your starting amount or your principal, 1250. E, of course, is a number. For R, I'm going to put 0.065. That's 6.5%. And it's for 8 years. So for T right here, I'm going to put 8. So the first thing you want to do, obviously, is take 0.065 times 8, and you will get 0.52. So your exponent is really 0.52. Alright, so with your calculator now you would type in 1,250, then hit your E button and this will pop up, and then type in 0.52 and then hit enter. If you do that, you will get this right here, $2,102.53. So you started off with 1,250 and you ended up with $2,102.53. So you gained how much? $750, $850, $857.53, I think. I did that in my head, but I believe that's accurate. Alright. No, that's not accurate. Let's see here. 700, 800, $802. I believe, and 53 cents. I think that's right, but anyways, you get the idea. If I'm wrong, I'm trying to do it in my head, it's no big deal. $852, I think. I believe would be right. Anyways, moving on. So, this is the formula you want to use for compounding continuously. Alright, moving on to number 47. Now this one's interesting. It's actually 2 problems in one. So let's divide this up into 2 parts or 2 spaces here. That's a really good line, isn't it? We'll fix that real quick there. Alright, here we go. Now, we're going to deposit $3,000, okay? But this one over here, both of them are 5% interest, okay? So 5% interest, 5% interest. However, the first one's going to be continuous compounding, so I'm going to put the word CONT for continuous. Over here, we're going to compare that with quarterly compounding, so I'm going to put QUART period. Alright, so over here we're going to find continuous compounding go. I'm starting off. I'm looking for the balance. It's A. My principal's $3,000. My rate is 0.05, and it's for 10 years, so my T is 10. So with the calculator, we're going to type in 0.05 times 10, which will give us 0.5. So now my entire exponent is 0.5. Now with your calculator, type in 3,000, then hit your E button, and this will pop up. Then type in 0.5. Alright, if you do all of that correctly, you're going to get $4,946. $4,946.16. Okay, so that's compounding continuously. Now, let's compare that with compounding quarterly. Alright, so here we go. First of all, A is your ending balance, your ending amount or your balance. B is your starting amount or your principal, 3,000. Over here we have 1 plus, now R of course is 0.05, 5%. N is the number of compoundings in 1 year. Since this is compounding quarterly, that means 4 times a year your interest will be found, and that's good. The more times that your interest is found, then the better off, then the more money you're going to make. So, quarterly compounding, that's 4 times a year. And of course, is 4. T is 10 years. So here's what I'm going to say to you. First of all, I would make this entire parentheses right here, all of this become one number. So with your calculator, if you'll type in 1 plus 0.05 divided by 4, you will get this right here. 1.0125. And of course 4 times 10 is to the 40 power. Bring down your 3,000. So guys, it really does become a calculator problem now. With your calculator, you would type 3,000, then parentheses, then 1.0125, then close your parentheses, then arrow, and then 40, and hit enter. And if you do that, you will get $4,930. $4,930.86. So there's the two differences. So as you can tell, compounding continuously is a little better. And of course, the longer you leave it in for, the better off it's going to be. You'll make more money compounding continuously than any other type of compounding, unless you're dealing with a different rate. In other words, 5% compounded continuously might not be as good as 8% compounded quarterly, because your percentage is higher. But if the percentages are the same, if your rate's the same, then you're compounding continuously will give you more money because the interest is being found more often. Alright. Okay, moving on, guys, to number 50, excuse me. Okay, 100 grams of radium is stored in a container. The amount of radium R in grams present after T years is given by this model right here. Alright, now learn how to read a problem and understand what they're saying to you, okay? They're saying to you that you can tell me how many grams of radium you have, and I'll tell you how many years have passed. Or you can tell me how much time has passed, I will tell you how many grams of radium is left, okay? As long as you know how much you started with. Now, I want to see how well you guys are really grasping exponential functions. Remember, we always say this is your ending amount over here, this is your starting amount right here. So what we're saying is that you did not need to know this, okay, to do the problem, but because there's 100 right here, that's like your A equals, PRT when we're talking about compounding continuously. I keep telling you this is your ending number, this is your starting number. Well, I know we don't have the exact same model, and I know that this is not an interest problem, but this is still your ending amount, and this is your starting amount. So we start off with 100 grams of radium. It also told you that right here. But if they had not told you that, you would still know it, because this is your starting amount when time is 0. Alright? Okay, so what do they want us to do? They want us to state how much radium is left after 10,000 years. So that means we're going to put 10,000 in for T. That's all we're going to do. So where the T is right here, I'm simply going to put 10,000. That's a long time, and there will still be some radium left over. Alright. Well, first of all, you take negative 0.00043 times 10,000, and you'll come up with this. Negative 4.3. Alright. So now with your calculator, if you'll type in 100, then hit your E button, so this pops up, and then negative 4.3, and then close your parentheses and hit enter. You will get this right here. 1.36 grams of radium, so that's how much is left after 10,000 years. 1.36 grams of radium. Okay, moving on to number 52. The amount of money in millions of dollars spent by the United States Postal Service from 75 to 90 can be modeled by this model here, where T equals 5 represents 1975. Estimate the amount of money the United States Postal Service spent in 1986. Alright, no problem, excuse me. Here's your model right here. Let's write that down. Let's use this model. Now, what does this model do for you? Well, you can substitute in a T. Okay, students, sorry I had to pause the video there, but anyways, what this function does is you can put a T value in for T and get out how much the post office spent, or actually, you can put in how much they spent and get out what year it was, okay? So either way is fine. Now here, they're saying estimate the amount spent in 1986. So we're going to put a number in for T and get out the amount that was spent. So here we go. It says right here that 5 represents 1975. So if 1975 is represented by 5, I'm going up to 1986. That's pretty simple. Add 5 years, so 1980 would be 10. Go up 6 more years, 1986 would be 16 years. Okay, so where the T is right here, I'm going to put 16. So I'm going to put a parentheses and put a 16, and here we go. First of all, I'm going to multiply 0.079 times 16. Let me grab my calculator. 0.079 times 16, and you're going to get 1.264. 1.264. So your exponent is now 1.264. So now with your calculator, type in 8679, then hit your E button, and this will pop up, and then type in 1.264, and then hit enter. And if we do all of that correctly, you are going to get the right answer, which would be this right here. 30,719.77 million. Okay, don't forget, M is in millions of dollars, so whatever you get out is in millions. Okay, or in other words, you can take this number here, 3719.77, and multiply it by a million, and you will have the correct exact amount. Alright, moving on. The next page is page 430. We're looking at 51 through 55, so here we go. Now, first of all, let's just stop and get this formula up here. I did not feel like I did a great job of teaching this when I went over this material, so let's get the model written up here we're going to use for number 51 here. Alright, we have this. KT, by the way, if you'll turn in your books to page 430, you will see directly above number 51 in the book, you will see they give you this model right here. Alright. Okay, now the S's, let's get this taken care of once and for all, okay? K is a constant. That means it's going to be a number, and you have to find that number. The only way to find that number is to have a scenario like we have here, where you know how long it takes for water to freeze in a certain environment, 4 hours, okay? So K is a number, time, T is your time. I would write all this down if I were you, and it has to be in hours, not minutes, not seconds, hours. Now these two S's here would be your surrounding temperature. Surrounding leave the answer up there. It really doesn't matter if you see the answer. Alright, and here we go. And I should have put this on the screen. I did not, but that's okay. If you'll turn your books to page 430, you'll see this. It says, you place a tray of 60 degrees Fahrenheit into a freezer that's 0 degrees Fahrenheit. The water cools according to Newton's law of cooling, okay? So 51 says, if the water freezes in 4 hours, what is your constant K? Alright, so listen to me carefully. We're looking for K, so we gotta fill everything else in, okay? Well, first of all, we're leaving the water in the freezer for 4 hours. So K is K, and T is 4. So I have K times 4, okay? If it's okay with you guys, I'm gonna go ahead and put 4K, because K times 4 is 4K, equals natural log. Now, your ending temperature, well, you're seeing how long the water freezes in 4 hours. So your water tray ended up at what temperature? 32. That's what the temperature is when freezing happens, okay? Your surrounding temperature is how cold the freezer was. Well, if you'll read up above number 51, it says the freezer was at a temperature of 0. So far, so good, not difficult at all. Your starting temperature, well, if you'll look up above number 50, it says the tray of water was 60 degrees. So that's your starting temperature. And again, your surrounding temperature is 0. So what we have is this. 4K equals the natural log of, now 32 divided by 60 is 0.53 repeating. I'm just going to leave it a fraction. I'm going to put 8 over 15 if you reduce it. Alright. There we go. Alright. And now to find K, divide both sides by 4. So K equals the natural log of 8/15 divided by 4. So here's how you would type that in your calculator. Hit your natural logarithm button, then 8 divided by 15, then hit enter. Be sure and hit enter. Then hit divided by 4, enter. And if you do that, you will get this right here. So now you found your K. So the rest of the time that we use this model for the next couple problems, we now know what K is. K is negative 0.157. Alright? Okay, moving on. Suppose you lower the temperature to negative 10 degrees Fahrenheit at this temperature. How long will it take for the ice cubes to form? Alright, well, let's take a look and see if we figure this out, okay? Well, first of all, for K, I now have a number. It's negative what was it? 0.157. So there's my K. We're looking for T because it says how long will it take. So we're looking for T. Equals natural logarithm of, okay, here we go now. All that we're doing is we're lowering the temperature in the freezer. Nothing else has changed, okay? So my ending temperature is still going to be 32 because I'm looking for how long it takes for the ice cubes to form, okay? So I'm still wanting the water to end at 32. That hasn't changed. However, the surrounding temperature is now negative 10, so it's minus a negative number. Negative 10. Now over here in the bottom, our starting temperature has not changed, but the surrounding temperature is negative 10, so minus a negative 10. So we really have this. Negative 0.157 equals, squeeze a T in there, T equals natural log of 42 over 70. Alright, now if you reduce that fraction real quick, let's see what you get. 42 divided by 70 is 3/5, or you could just use 0.6 because it did not round, and it did not repeat or continue on, so I'm just going to put 0.6, okay? So there we go. Now to solve for T, divide both sides by negative 0.157, so T equals the natural logarithm of 0.6 over negative 0.157. So in your calculator you would type, excuse me, natural logarithm of 0.6, enter, divided by negative 0.157, enter, and you will get this right here. 3.25, and of course time is in hours, so that's that's how many hours it would take. Alright, moving on to 53. Suppose the initial temperature was lowered to 50 degrees. Remember, the other initial temperature was 60 degrees. If the freezer temperature is at zero, how long will it take for the ice cubes to form? Okay, guys, piece of cake. I mean, no problem at all. First of all, we know what K is already. Negative 0.157. T is what we're looking for because it says how long will it take. And then natural log. And then what? Ending temperature. Well, my ending temperature is 32 because I want ice cubes to form. My surrounding temperature now is back up to zero. It says if the freezer temperature is zero. Alright, now my starting temperature is no longer 60, it's 50. And of course my surrounding temperature is still zero. So I have this negative 0.157 T equals 32 over 50. Of course, let's reduce that very quickly and see what we get. And we get 16 over 25. Actually, it comes out to a decimal that doesn't round or repeat, just 0.64. So I'm going to leave it like this, okay? Now divide both sides by negative 0.157. So T equals the natural logarithm of 0.64 over negative 0.157. So here we go. With a calculator, you would type in natural logarithm of 0.64, enter, divided by negative 0.157, enter. And if you do that correctly, let me look at my notes here, you will get 2.84 hours. And all of these answers have been, I've checked these, they are correct. So 2.84 hours. Okay, so it's kind of interesting. If you look back here, you lowered the temperature of the freezer 10 degrees, but it took longer, 3.25 hours, than if you just would have simply, instead of lowering the temperature of the freezer, leave it at zero, just use water that's 10 degrees cooler, 50 degrees, and it actually takes less time. Very interesting, okay? Alright. Okay, moving on. Number 54. A package of frozen steaks are taken out of the freezer and left at room temperature. The temperature is related to time in this model here. So here's the temperature of the steaks, or of the package, based on hours. T is hours by this model. So guys, this is a pretty simple problem. They've given you everything. How this function here, you can either tell me the temperature of this package, I'll tell you how long it's been out, or you can tell me how long it's been out, and I will tell you what the temperature of the package is. The question is how long will it take the package to reach a temperature of 60? So they're giving you the temperature, you're looking for time. So time equals negative 3.8 natural logarithm of, put 60 in for T, 60 minus 70 over 24 minus 70. Alright, well guys, that's negative 10 over, that's negative 10 over negative 46. Alright, now if you reduce that, you'll get, let's see if that comes out to a nice decimal. Hopefully it does. No, it does not. Okay, so we're just going to leave it a fraction, and negative over negative is positive. So we end up with T equals negative 3.8 natural logarithm of positive 5 over 23. So guys, we know how to type this in. Simply type into your calculator negative 3.8. Then type your natural logarithm button, and this will pop up. Then type in 5 divided by 23, and then be sure and close your parentheses. Alright, and if you do that correctly, I'm just checking here to make sure we've not made any mistakes. If you'll do that correctly, you will get this right here, 5.799, and they've rounded 5.8 hours. So if the temperature of the frozen steaks is 60 degrees, then the package has been out for 5.8 hours. Guys, we're just taking all kinds of scenarios and practicing using logarithms. Alright, number 55. From 81 to 90, the amount A spent on salaries and wages for national parks for employees can be modeled by this model right here. This is a really easy problem, students. Where T equals 1 9 to 81. So with this model here, you can give me a year and I can plug it in and get out the amount spent. Or you can give me the amount spent and I'll tell you what year it was, okay? About how much money was spent on salaries and wages in 1984. So all I'm doing is putting a number in for T. Now, if 1991, if T equals 1 represents 1981, then T equals 4 has to represent 1984. So if there's a T, I'm going to put a 4. So I have 286.52 plus 7.25 times 4 plus 27.51 natural logarithm of 4. You could type this whole thing in just like it is, students. And that's exactly what I would do if I were you. You can take your calculator and type this in. Type in 286.52 plus 7.25 parentheses 4, close your parentheses, plus 27.51, then push your natural logarithm button, then parentheses 4 parentheses, and hit enter. And you'll get out approximately around 354, but remember, that's in millions, because it says A is in millions of dollars. So there it is, you found it. That is your amount that is spent on salaries and wages in 1984 for the National Park Service employees. Okay, there we go, guys. Not that difficult. You got to learn. Listen, you've got to learn to look at a model, figure out what the variables stand for, and then plug in or substitute in the correct value for the correct variable. All right, moving on to our last page, which is page number 439. I'm going to quickly turn over there. We're looking at 4 problems, 47 through 53 odd, 47 through 53 odd, and here we go. Number 47. You deposit $1,000 in an account that pays 5% interest, compounded continuously. Now, in the previous problems we've done, they've asked you to tell how much money you have at the end. What's the balance? Well, now they're giving you the balance. They're saying, how long will it take? Well, these are pretty cool problems. If you know how much money you want to invest every year to have out a certain amount of money for retirement or whatever, these can be really helpful formulas to use. So we're dealing with compounded continuously. So here it is. All right, now you're starting off with 1,000. So that's my principal, my starting amount. You're ending with 1,500. That's your balance or your ending amount. And then, of course, you have E. Your rate is 0.05. And T is what you're trying to solve for. Well, guys, excuse me. This is called an exponential equation. We have learned how to solve these. I have taught you how to solve these. Remember, you determine the base. There's the base. You determine the exponent. There's the exponent. And you get all that by itself. That's step 1. So we must divide both sides by 1,000 first of all to get this all by itself. So if you divide both sides by 1,000, you do get 3 over 2, or exactly 1.5. So divide both sides by 1,000 and you'll get 1.5 over or equals E to the 0.05t. Everybody see what I did? I divided by 1,000 and divided by 1,000. These canceled and this reduced to 1.5. Now, the next thing I'm going to do is step 2 is to take the logarithm of both sides. I'm going to put a logarithm here, leave a space, take a logarithm here. Now, what is the base of my unknown? Here's my unknown, here's my base E. So I put an E here and an E here. Then bring down this entire side. Bring down this entire side. And then here we go. First of all, you simplify this over here using your logarithmic rules. Whenever this number matches this number, so everything's gone except the exponent. So we're left with 0.05t. And over here, logarithm base E is the same thing as natural logarithm of 1.5. So let's clear a little space here. And let's pull this up and continue to work. We're almost done. The last step is get t by itself, so we're going to divide both sides by 0.05. So I have the natural logarithm of 1.5 divided by 0.05 equals t. natural logarithm of 1.5, enter, divided by 0.05, enter, and you will get this. Sorry about that, you will get this. Not sure what I did there. You will get this right here, 8.11 years. So that's how many years it's going to take you to go from 1,000 to 1,500. Alright? Okay, moving on, number 49. Same thing, only now it says is a compound and continuously. Yes, it is. Okay. So same thing, only now we're going to have compounding continuously, and our money is going to double. Alright? So here we go. We're dealing with compounding continuously, so here's your model. Now, A is your ending amount. Now you're starting off with 200, and you want to know how long it'll take to double your money. So if you're starting off with 200, then your ending amount will be 400. Your starting amount would be 200, and then e to the 0.07 t. So there we go. So students, we're solving for t. I had to pause the video there, so I'm not sure exactly what I said last, but here's our model. We're now solving for t, okay? So, step one, when you have an exponential equation, is know where your base is, know where your unknown is, your exponent, and isolate those. So we must get rid of the 200, okay? That's step one. Step one is isolate the base and its exponent. So we're going to divide both sides by 200. If we do that, we're left with this. Alright, now we're going to take the logarithm of both sides. The base, here's my unknown, the base of my unknown is e, so put an e here and an e here. Bring down this entire side. Bring down this entire side. And here we go. On the right side, whenever this number here matches this number here, everything's gone except for this. So we're left with 0.07t. Over here, a logarithm base e means a natural logarithm of 2. Now divide both sides by 0.07. So the natural logarithm of 2 divided by 0.07, all of that equals t. So with your calculator, type in natural logarithm of 2, enter, divided by 0.07, enter, and you will get the correct answer, which is 9.90 years. Okay, so it take about 9, almost 10 years for your money to double. Alright, okay, moving on. For 1960 through 1986, the amount of municipal waste in pounds per person per day processed for energy recovery in the United States can be approximated by this equation right here, where t equals 0 represents 1960. So what we have here is a model that in which you can tell me the amount of waste per person. I will tell you how long it took, or you can tell me what year it is, and I will tell you how much waste per person we had in the garbage system. Okay, so here we go. Here's my model. They're telling us that we have 0.22 pounds per person. That goes for your waste right here. So for W, I'm going to put 0.22. And then here we go, guys. It's back to work again. We have an exponential equation. Here's my unknown right up here in the exponent. So I want to isolate the base and the exponent. So I must get rid of this number here. So I'm going to divide both sides by 0.007. Alright, now if we do that correctly, we're going to come up with this number right here, rounded. I really don't like to round before the problem's over, but I'm going to have to. In this case, 31.42857 should be sufficient. So I divided both sides by 0.007. Alright. On the right side, I'm left with e to the 0.0051 t squared power. Now, I've isolated my base and my unknown, so now I'm going to take the logarithm of both sides, okay? So put a logarithm and a logarithm. And the base of my unknown is E, so I'll put an E here and an E here, okay? Now bring down this entire right side over here. Bring down this entire left side over here. And there we go. So now we have this. Your base matches your base, or this number matches this number. So you're left with the exponent. Logarithm base E is the exact same thing as natural logarithm of this number right here. So we'll bring that down. Alright, let's create a little space here real quick and continue on. Now obviously, I'm going to have to divide both sides by 0.0051 to get t squared by itself. So the natural logarithm of 31.42857 divided by 0.0051 equals t squared. Everybody see that? I divided both sides by 0.0051. Now I have a t squared, so I must take the square root of one side. If I take the square root of one side, I must take the square root of the other side. Okay? Now, if I take the square root of the left side, I'm going to be left with just t. If I take the square root of the right side, normally you would put plus minus. But this is a word problem, and there's no way time can be negative. Excuse me. So we're just going to use the positive. So here's what you do with your calculator, okay? Type into your calculator natural logarithm of 31 point, and I'm going to actually type this in with us to make sure we didn't make a mistake anywhere. Natural logarithm of 31.42857, enter, and then divide it by 0.0051, enter. And then take the square root of that number. However your calculator lets you do that, you should have 676.0230102. Now take the square root of that number, and you will get 26.0004425, so 26. Now, that is not your answer. It did not say how long would it take. It said in what year. In what year. So 0 represents 1960. That's what it says right here. So 10 years later, that would be 1970. 10 more years later, up to 20, it's 1980. And then 6 more years, that would be 1986. Okay, so in 1986 is when the amount of garbage or waste per person is to be 0.22 pounds per person. Alright? Okay, let's move on to the last problem. We're finally finished. Now in this problem here, you will want to look to the left of the problem, okay? So make sure you're on page 439 and look to the left. You'll see a drawing, okay? We're going to need that figure. Okay, here we go. Oceanographers use the density D of seawater to obtain information about the circulation of water masses and the rates of which the waters of different densities mix. For water with a salinity of 30%, the water temperature T in Celsius is related to this, to the density by this model right here. So we're assuming the water we're looking at to the right there in your book, okay, is has a 30% mixture of salinity of the water. Salinity is 30%. Okay, we're assuming that. Find the densities of the sub-Antarctic water and the Antarctic bottom water shown in the diagram. Okay, so first of all, before I slide this up like this, let me point some things out to you. Okay, these problems all sound so difficult, and they're just really so simple, guys. You're just figuring out what each variable stands for, then making a substitution. Okay, so here we go. Even this last problem seems so difficult, but we figured out what each variable stood for, made our substitution, then solved. Okay, now, so here we have a temperature given, and we have the density of the water. So you can tell me the density of seawater, and I will tell you the temperature, or you can tell me the temperature, and I will tell you the density. Now, we're trying to find the density. That's what we're looking for, okay? We're looking for the density right here. So if we're looking for the density, then they must give us a temperature somewhere, right? They must. Well, if you'll look to the left in your book, I'm going to raise this up. If you'll look to the left in your book, you'll see they give us temperatures, alright? And I'll show you those in just a second. Here's my model. T equals 7.9 natural logarithm of 1.0245 minus d plus or positive 61.84. Now, first of all, they want us to find the density of the subantarctic water, so would you please look to your right and notice the subantarctic water is the very top level. And if you look at that, it says it's 8 degrees Celsius off to the right side there. It's in the blue water off to the right, and it says 8 degrees Celsius. Okay, so we know the temperature of this water is 8. So where the T is right here, I now know that I can put an 8. Alright. And now look what I have, students. I have a logarithmic equation because I have an unknown right here in the argument. Okay? So students, if I have a logarithmic equation, then I know the first thing I have to do is isolate the logarithm. So here's the words. Here's the argument. Everything else has to go. This number has to go, and this number has to go. Alright? So let me bring over the positive 61.84, make it negative. So this is now gone, and I'm going to be left with negative 53.84. Next, I'm going to divide both sides by 7.9. Let me grab my calculator here. Negative 53.84 divided by, and I just messed that up, so hold on 1 second. Divided by 7.9 is going to give me a pretty big decimal. I'm going to round that to negative 6.81519 equals natural logarithm of this whole argument here. Now what I've taught you students to do is next write the logarithm exponentially. Okay, so e is right here. We're going to write this exponentially, so it will look like this. E to the negative 6.81519 power equals 1.0245 minus d. Remember guys, this right here, logarithm base AB equals c can be rewritten as b equals a to the c power. That's called writing a logarithmic expression exponentially, and that's what I've done here. Here's my logarithmic expression. My base went over here. This became my exponent, and my argument, which is all of this, is all by itself over here. Okay? So, I've written it exponentially. So now to solve this, it's really, to be honest with you, pretty simple. I mean, all I have to do is get d by itself, and I should be doing pretty well, okay? So in order to get d by itself, I've got to bring this number over here. It's a positive number. Bring it over and make it negative. So e to the negative 6.81519 minus 1.0245 equals negative d. So I'm going to type all this into my calculator real quick. Let's see what I get here. E to the negative 6.81519 enter minus 1.0245 enter, and I get this right here. Negative 1.0234 equals negative d. Well, there's a negative 1 here. Divide both sides by negative 1, and both sides become positive. So there's my answer, and that is the correct answer in the book, okay? So, that is the density of the water, and of course when it says density, you would label that grams per cubic centimeter. Okay, so it's how many grams per cubic centimeter. That's the density. So 1.0234 grams per, what's a cubic centimeter? Let's see. Grams per cubic centimeter. So grams slash, that means per, grams per cubic centimeter. Alright, let's take a look at the next one and we're finally done, okay? They also want us to find the density of the Antarctic bottom water, okay? Shown in the diagram. So it's going to be the exact same model again. T equals 7.9 natural logarithm of 1.0245 minus D plus 61.84, okay? Now we have to know the temperature, so if you'll look at your diagram to the right, the very bottom level is Antarctic bottom water, okay? And look to the right of that, the temperature is 0 degrees Celsius, okay? So for my temperature right here, I'm going to put 0, alright? So this is gone. I'll put a 0 here. Well, here we go. Now you notice I have a logarithmic equation. I know that because I have an unknown in the argument of the logarithm. So step 1 is to circle the words in the argument. That's what you have to get all by itself. So we must get rid of this, and we must get rid of this, alright? So students, let's bring the positive 61.84 over, make it negative. So now I have negative 61.84 on the left side equals, and of course we're left over with this right here. Now we're going to divide both sides by 7.9. So we're going to divide by 7.9. Divide by 7.9. Okay? Let me grab my calculator real quick. And if we do that correctly, negative 61.84 divided by 7.9 will give us a very long decimal, of course. Negative 7.82785. 2785 equals, and of course now the 7.9 is gone, so we're left with this right here. Alright, let's erase all of this and get some more space, and let's continue on. Now, what I've taught you when you're solving a logarithmic equation is, first of all, isolate the logarithm, which you've done. Secondly, I've taught you to write it exponentially, so we're going to write it. The base here is an e. We're going to write it exponentially, so I have e to this power right here equals the argument right here. Right there. Alright? So there we go. Now bring this number over to the left side and make it negative, okay? So I have this number here minus this number here equals negative d. So with your calculator, let's type all this in and get a really big decimal, okay? So I'm going to type in my e button and then negative 7.82785, enter, minus 1.0245, enter, and I'm getting this right here. I'm going to clear off some space up here. I'm getting negative 1.0241 equals negative d. Well, if both sides are negative, just make both sides positive, and we're fine. D equals 1.0241, which is the correct answer. So you would write your answer 1.0241. What was it? Grams per cubic centimeter. Grams per cubic centimeter. Okay, guys. All right. I hope that this video has been a help to you guys. If you have any questions, don't hesitate to